Problem 35. If f of x is given and y is equal to log of x, then the frequency function of x for all real numbers is. So question 35 is what we need to find the distribution of y, which is log of x. So here I give two solutions. Here the f of x, so capital F, is the probability that x is less than some value x, which is the cumulative here. And then I make a u substitution and solve, and then plug in the limits. We get 1 minus e to the x squared over 2. Okay, I do that because now let's find the cumulative distribution function of y. So like if we know this, then we can take its derivative. So this is y less than little y, but capital Y was log of x. So you take e to the both sides. Well, we know this cumulative distribution function is this. So then we plug it in. Now to find the density of y, we take the derivative of our cumulative distribution function. So that means take the derivative of this. So the derivative of a constant is 0. So then we take the derivative of this, which is this, and then times the exponent. So it's a chain rule. And we get e to the 2y minus e to the 2y over 2. Okay. And then a second way to solve this is if y equals log of x, we can kind of back solve it for x, so it's e to the y. Take the derivative of x with respect to y, so it's e to the y. Now, the transformation formula is f of y is equal to f of x, where you plug in this x for x, and then take it times absolute value of the Jacobian, which is this, and plug them in, and we get this density, which is the same. Problem 36. A sequence of coin tosses, head, tail, tail, head, tail, can be related to the sequence 1, 0, 0, 1, 0 and used to generate binary numbers. If an unbiased coin is tossed 9 times and the related sequence of zeros and ones is recorded, what's the probability that the binary number represented will exceed 256? So, problem 36, we have a series of tosses that can be replaced by ones and zeros, and we want to find that what's the probability that we exceed 256. So here is just a quick understanding how binomials are represented. You know, if we let bi be 0 and 1, and that goes from 0 to n minus 1, then in our example where we had 9 flips, so we go from 0 to 8, so each, flip 1, 2, 3, 4, etc. Then a binomial number is, this is either 0, 1 raised 2 to the 8th. This is either 0 or 1, 2 to the 7th. And you add those up. And anyway, that's the binary representation of this. Well, here, to get 256, this last coefficient, B8, has to be 1. And then the rest have to be 0 to be 256. So, if this is our representation, 1, 0, 0, 0 equals 256. So then, to exceed 256, that means any one of those has to be a 1, and then we exceed 256. But each of those are Bernoulli trials, so it's either a 0 or 1. So if any of those are 1, we exceed it. So we need to find the probability that any one of those is 1. Well, if we let x be those coefficients from BI from 0 to 7, and each one of those is a Bernoulli, then the distribution of x is a binomial from 8 to 1/2. So we want to find the probability that B8 is 1 and x is greater than or equal to 1. So any of those are 1. Well, since this one event is independent of these 8 events, then we can break them up into this. Well, this carries over, and remember that the trick of 1 minus, that comes in a lot. So this is equal to 1 minus probability that x is 0. Well, that's pretty straightforward to plug into for a binomial, and the probability that B8 is 1 is 1/2. So 1 minus, and this is the dense distribution or probably mass function for a binomial. Plug it in, and we get 1/2 minus 1/2 to the 9th. Problem 37. The mean of a certain normal distribution is equal to the standard deviation of the mean of a sample of size 200. What is the probability that the mean of a sample of size 18 will be negative? So 37. So here, this is interesting. So we know x is distributed normally with some mean and some standard deviation. Y is normally with some mean and standard deviation. Y bar is distributed with the same mean, and the standard deviation is the standard deviation of y divided by the square root of the sample size, which is 200. And it says that our mean is equal to, the mean here is equal to this standard deviation, which is that. So then, now we have a sample size 18, calculate the mean. Well, that is the normally distributed with the same mean, and it has a standard deviation of sigma over the square root of 18. That was our sample size. But we know that our mean is this, so we could plug in that for there. And we want to know what's the probability that our sample mean is negative. Well, if we standardize this, so subtract the mean from both sides and then divide it by the standard deviation of both sides, we get this. So this is a z variable. This mean was that. So then those reduce down to this, which then probability z is less than minus 0.3 is 0.3821. Problem 38. If the joint probability density function of x1, x2 is 1, then the moment generating function of the joint distribution is so problem 38. We need to find the moment generating function of x1 and x2. So the definition of a joint moment generating function is the expected value of this. So we plug that into our, we integrate over all possible values of x1 and x2 times the density, but that was 1. Well, since we're integrating with respect to x1 first, let's factor out x2 and integrate this. Well, that is integral of this, so plug in the values. Well, Now this is constant, so you can take it out of the interval and just integrate with respect to x2, and you get this, and then that simplifies to this, which is one of the answers. Problem 39. The mortality of a certain type of transistor is such that the probability of its breakdown in the interval of t to t plus dt is given by this equation. If 10 of these transistors are taken at random, then the probability that the 10th transistor will break down will do so during the time interval v plus dv is. So here it talks about a certain mortality, so the density of T is given by this. So let's find the cumulative density, which is capital F of T. You integrate from 0 to T and you come up with this. So now let's think about this. We do this two different ways. So I use the theory of order statistics. So if our 10 samples, and these are the times that they fell, we don't know which one is going to last the longest or which one is not. So in order statistics, we take the smallest one and call it T sub 1 and put parentheses around it. Then we take the second smallest, T sub 2. And then wherever the longest one, that's called T sub 10. So this is the longest. And we want to find the density for that, the instant probability for this, the function. Well, the nth or the largest order statistic is this. You take what order statistic it is, n, so that's actually 10, probably should have put a 10 there. The cumulative distribution of t raised to the n minus 1 times its actual density. So plugging in these values here, we get this is the density of the largest order statistic. Now to calculate this a different way, this is f of capital T of 10. This is the cumulative distribution function of the largest value. So that's the probability that we're less than some t. That's cumulative distribution function. But if the largest is less than t, that means all the others have to be less than t. But each of those events are independent. So that's the probability that the first trial is less than t, the second, the third, all the way up to 10th. They all have to be less than t. Well, that is the cumulative distribution function, which is this, raised to the 10th power. Now we take the derivative of this capital F, and then the derivative of that, the 10 comes out front, reduce it by 1, take the derivative within there, we get this, and then the derivative of that, and then they integrate to the same thing. Number 40, let x1 through xn be a random sample of size n drawn from a normal population with mean 0 and variance 1. Let x1 through xn be an independent random sample of size n drawn from an unknown distribution. Given that x1 equal to little y1, x2 equal y2, yn equal yn, and that the y's are not all 0, what is the conditional distribution of the sum of yx divided by the sum of y squared? Okay, here's example 1 of 8, question 40. We're given that the x's are normally distributed, y's are independent, identically distributed from some unknown distribution, but we want to find the density of this given the xi values. So that means these are constant. So this is going to be, it's a linear combination of the x's. This is constant, those are constant. So any linear combination of normal random variables is normal. So we just need to find the mean and the variance of this, and then we know the distribution. So the expected value of this combination is this. Now the bottom is constant, so we bring it out of the expectation. Then we take the expectation in, but notice that yi is a constant, so we take it out. And the expected value of the yi's is 0. So this overall expectation is 0. So the variance, this is a constant, so we take it out and square it. And then we're still left with the variance of this. So that can be taken in, but then this is a constant, so we have to square it. And then the variance of each xi, which is the variance is 1. So this, we're just left with the sum of yi squared. Well, that cancels with one of those, leaving this. So it's normal, 0, variance this. Problem 41. The three angles of a triangle were measured to be A equals 55, B equals 60, and C equals 62. What are the least squares of the true angles alpha, beta, and gamma? Remembering that alpha plus beta plus gamma equals 180. Problem 41, we're given a triangle and we estimate each angle to, with A, B, and C, and we want to find out what the least squares estimate of those angles are. So remember that we're trying to find angle alpha, beta, and gamma, and we know that this restriction that they add 180. So to minimize the square difference of our estimate minus the true angle squared, estimate minus the true angle, oh, I could have left out the I, just call it A, B, and C. Estimate squared. So to minimize this, we we have to place this restriction in this equation. We do that by letting gamma be the 180 minus alpha minus beta. Now we take the derivative with respect to alpha and then set it equal to 0. Take the derivative with respect to beta, set it to 0. So we have two equations, two unknowns. The unknowns are alpha and beta in here. The B, C, and A are the estimates of our angles. So we can plug in our estimates, and then we come up with alpha hat is 56, least squares estimate of beta is 61, and the least squares estimate of gamma is 63. Problem 42. A fair coin is tossed at random 100 times. What is the approximate probability that the number of heads will exceed 60? Problem 42 is we take a coin and toss it 100 times, and we want to find the probability that we exceed 60. So notice that each xi is binomial. So the sum of those xi's is also a binomial because the probability parameter is the same in each. So it's a binomial 100 to 1/2. Well, calculating the probability that y is greater than 60 is we're gonna have to sum a lot of those variables, which is not really doable by hand. So we use a normal approximation. So note that y, because it's a sum, so the central limit theorem comes in. It approaches to a normal with mean NP and NPQ, and you can find the variances this way. So the probability that y is greater than 60, this is under the binomial distribution. Now when we assume it's normal, we have to add a continuity correction of 1/2, and then from here we subtract the mean and divide by the standard deviations to both sides, and this side is a z, and This is 2.1, so probability Z is greater than 2.1 is 0.079.